Hello friends, my name is Jayakumar Ravindran. I am currently a PhD student in the Institute of Mathematical Science Chennai. I am planning to upload a series of videos about group action. Already I did it in Tamil version. Now I wanted to do in English version. Many people asked me about English version. So this is one of the very important concept in the whole mathematics. Okay, let me do without any further disturbance. Let me do. Okay. Anyway, I wanted to do like the oral version. I do not want to do complete version. Okay, I do not want to replace any traditional teaching. Traditional teaching has its own merits, so it's better to do. It's kind of a complementation of the traditional method. You have to read books to understand even completely. Okay, let me start with the definition. Okay, definition. So G group, I'm going to be vague only because I do not want to, again I'm saying, do not want to replace any traditional method. X non-empty set group action on X, we mean a function from G cross X to X satisfying this condition. I'm just denoting like this, satisfying this condition. First condition, identity comma X equal to X for every X belongs to X. Second condition, GH acting, this is group acting, group multiplication, then acting is same as first H acting then G acting. Okay, these two conditions are the fundamental thing. Okay, again I'm telling you, first condition says the identity acts trivially, does not move X. So group action means group is there, set elements are there, so element G acts and moving. It says that the X cannot be moved by the identity. Identity will not move the X. This is very important condition. Both conditions are very important. Second, you GH, you do the multiplication in group. This is happening in the group. Then act X is same as first you do, then you act X. Both are same. Okay. So after this definition, I wanted to then we say X is G set. Such action happened, then X is called a G set, and we denote like this. Okay, let me do the permutation representation. What I mean by permutation representation. Okay, group, this is kind of associative law, okay, group action and permutation representation. I am following Michael Artin book as well as Professor K.N. Raghavan notes. Is from Institute of Mathematical Science. In his website you can find a PDF about this thing. Okay, suppose X is G set, that means G acting on X. Then let G belongs to G fixed. Okay, I am defining a function from X to X like this. That is nothing but G comma X. This is a well defined function because it's restriction. So my claim is it is invertible. Okay, let's see how. Definitely this function depends on this G, hence the inverse must be depends on the something about G, so we can guess like a G inverse. Let me do one side, the reverse side is easy. Okay, G comma X, that is G inverse G comma X. But remember the second law. Remember the first condition. Okay, so the reverse also true because of the symmetry. Okay, so finally what we are getting, G phi G is invertible for fixed G. Okay, that means phi G belongs to Sx, that is same as theorem of X. It is nothing but function from X to X which is bijective or invertible, set of all function from both are group. Okay, So finally we are getting a function from here to here. G goes to Fiji. Okay, so remember that this is group, this is also group under multiplication, sorry, function composition. We are in a good situation now, we no longer in a set. And now let's see. Okay, once you define such a function from one group to another group, it's natural to ask whether this is homomorphism or not. We will prove this is homomorphism. What do I need to prove? GH goes to phi GH. Phi GH act on X is nothing but GH comma X. But remember the second condition that says that this is true. That is nothing but phi G composite G HX. That is nothing but phi G H comma X. That is G HX. Both are same, right? So GH goes to phi GH, G goes to phi G, H goes to phi H. This satisfies a homomorphism condition. So we are in a good position. Finally, what I proved actually, G acting on X, the group action, somehow related to homomorphism Sx. One direction we proved. Another direction we can reversely ask the question. Let me prove the question, the reverse way. What is the reverse way? I will give you the homomorphism from this thing. Let's say capital Phi homomorphism, group homomorphism. Can we give an action on the set? Yeah, that is true. I am going to give action on the set. How? G cross G to X, like this. Let me verify this is a group action indeed. Identity goes to, by definition, but this is nothing but ID on X, because this is homomorphism, group homomorphism. This is ID on X. That means X itself. So IX equal to X for every X belongs to X. Now let's do the second condition. Phi H on X. This is phi G composite phi H on X. So that is equal to phi GS, because this is homomorphism. So that is nothing but, so the both conditions are satisfied. So this is indeed a group action. So that means giving a group action is same as giving homomorphism from G to Sx. This is nice, you know. This is both sides are group, so this is very nice. Now I am going to define a kernel of action. Kernel of action. Suppose we have a group acting on the set. Kernel of action. Before that, let me do the stabilizer. That X belongs to X. Stabilizer of X equal to set of all G belongs to G, such that Gx equal to X. See, this condition says that I am collecting those G's which actually does not move the X. When G acting on X equal to X does not move, definitely identity will be there, and we can prove this is subgroup. In fact, the kernel of action I am going to define like a intersection of all stabilizer. This is indeed a normal subgroup. To prove that, we use this. Okay, the word I wanted to justify why there is a kernel. Indeed, we are going to prove this is a normal subgroup. Okay, claim. One direction I will prove in the claim. Kernel of action is same as kernel of permutation representation. What is permutation representation? G act on X, then we have this thing, na, homomorphism. That is a permutation representation. Okay, let A belongs to kernel of action That means A acting on x equal to x for every x belongs to x. This is the definition of kernel of action. How that is defined? G, that is, let's say A, phi A of x equal to a comma x, that is equal to x. That means implies phi A is ID map. That means ID on x. Hence, what we are getting actually, this maps here A goes to ID map. So this A belongs to the kernel of this phi. Reverse direction is easy. You just prove it. This is very important to prove that is going to play a vital role in later on the subjects. Okay. All I wanted to know that giving action is same as giving homomorphism. This is what I wanted to do in this video. Okay. Later on I will give you the different example.